Welcome back. I would like to cover a very important topic, which is called constraint function construction. And I will cover this in two different parts, part one and part two, because I don't want this to be a long video. In part one, I mentioned about the general approach with some examples, and part two, I will dive into some important details that you should know or be aware of. All right, first of all, what do we mean by constraint function construction? Least-squares is a great tool to generate a parametric or a non-parametric function model that estimates the relationship between a dependent variable and an independent variable. What I mean by estimate is, right, you have different points and you find the function that passes from by minimizing the error between that function, that model, and these estimates. So it is an estimate, and it's a great tool that we use in many areas of machine learning and control theory. But it is an estimation. For some specific applications, you need to generate exact function that, for example, passes exactly through these points, right? For example, you have a robotic arm, you want to grasp precisely an object, or if you are doing a landing, let's say you have you want your quadcopter to land to a very specific place, you would like the quadcopter to be there exactly at the exact desired time. Let me give you two examples why we call this constraint function construction. The first constraint coming from, you want that function, you first of all have two data points. In control theory, we say waypoints, more precisely in motion planning. And let's say we are dealing with a certain application that we must be there on that exact point. So that at y equals to t0, we must be at p0, and y equals to t1, we must be at p1. So these are the two constraints that we would like to enforce to a given function. Now, the second constraint may be some level of smoothness. When we are passing through these points, the derivative of y needs to be 0. Right? For example, this appears in the landing problem. Not only velocity, let's say y denotes the position. By the way, I call it y, but since the function is p, you think this as p dot instead of y, p, or you can think p as y. Sorry for the typo. Basically, right, when you are going from point A to point B, and if you want your velocity to stop, you also would like to add these constraints, two more constraints. And for quadcopter landing problem, let's say you are starting from some point and you are landing, let's say P represents the altitude, you would like to be at this point, and at this point, basically also your acceleration needs to be 0, additional constraint. So to wrap up, constraints depending on position, velocity, and acceleration has some requirements. They enforce constraints, curve fitting, or function generation. I also would like to mention, if we don't have velocity constraints, then a line equation can perfectly pass through these two data. Once you also include these velocity constraint, right, you have a function looking like S that fits into data. All right, and in this case, this is the line equation, and this is the equation that will fit to these two points. All right, let's dive into the details. Don't forget, if you like these series, subscribe, turn notifications on, and give a like. This is really motivating, and also leave a comment. Your comments are also important. That really, I up to now, I answered all the comments. And in detail so that they help me, they motivate me, and I am doing for non-profit purposes, and these type of likes and comments really motivates me to cover more material for my for you guys. All right, so let's start simple with 2 points I mentioned. Now I would like to give the mathematics behind this. At x1, I want to be y1. At x2, I want to be at y2. All right. So we need an exact function model that satisfies these 4 constraints, right? At y1, this is the function delta that I am going to define, and I will teach you how to define precisely. Y1 at x1, I will to be y1 to be x2. Let's add 2 more constraints similar to time derivative. Since we are depending on x, I am using prime. Basically this function's derivative with respect to dx should be 0 here, right? It will be smoothly, as well as this function's derivative should be 0 at delta prime at x2. So we have 4 constraints. If we use polynomials, 4 constraints imply that we at least need 4 weights. You can use more than that, 4 will be sufficient. So I am choosing delta to be a polynomial function starting from w0, w1x, w2x to the power of 2, w3x to the power of 3. You have 4 weights because you have 4 constraints. Let me give you as a homework after you watch this video, also include this. x1 and 0 prime prime x2. In this case, you need to include w4 x to the power of 4 plus w5 x to the power of 5. You need 2 more weights because in this case you are going to have 6 constraints that will imply 6 weights. We also mention here that prime is basically taking the derivative with respect to x. This becomes 0. w1x becomes w1, this becomes 2 w2x, so on and so forth. I would like to call this star equation star equation. Now I would like to use these 2 equations within these constraints, right? So basically using this and this together, you have y1 equals to y0, y1 at x1, right? x1 and I'm using x1 to the power of 2 and x3 to the power of 3. I am using the same equation for y2 point. You have this expression. I am doing the same for this prime equation. Basically 0 equals to delta prime at x1. 0 equals to, this is the delta prime. So 0 equals to w1. 2w2 x1 and x1 to the power of 2. I am doing this for x2 as well for this constraint. At the end of the day, you can represent these 4 equations like y vector, y1, y2, 0, 0, w0, w1, w2, w3, and this omega matrix. And you can solve this as, you can get the values for w's by w equals to theta inverse y. That is because y equals to theta multiplied by w. You can find w by inverting omega and get y. And in this case, omega should be invertible since you use for the number of constraints given, you use the equal number of weights. All right. The very first example, MATLAB example, is here. I choose these 2 points, x1 and x1, y1, x2, y2, which are given in code here. I construct omega matrix exactly the way I construct here. Here is the y, and here is how I find w. And then I evaluate this function between x1 and x2, and this is the exact fit. Now, once you plot this MATLAB code, you are going to see that we touch 5 and these two data points precisely. dy over dx is 0 here and dy over dx is 0 there. So this is kind of a nice fit. The natural question is, you may have, well, what happens if you have more than 2 points? Now I would like to connect 3 points, and the answer is really simple. I use the same code. Now I have 3 points shown here or here. I am going to do this process that I showed you in the previous slide twice. First, I am finding an omega y1 and w1 that connects these 2 points. And then I am using exactly the same formulation, but instead of using x1 and x2, I am using x2 and x3. Instead of using y1 and y2, I am using y2 and y3. So this is second part of the code is connecting x2 and x3. Then I am basically running the code like, for this region, if, right, this is x1, this is x2, if xp is less than x2, use the first w1 function. If xp is greater than x2, use the second w2 function. So it is like I am connecting these two composite functions within each other. And basically, if you run this code, this is the first fit, then it is the second fit. This way, you can iteratively connect n data points, which is a great tool with some smoothness properties that you have. Let's add another point iteratively. I now have, I am doing the same thing. Again, you can automate this code and you can connect n number of points. Omega 1 is basically connecting these 2 points with each other and W1. W2 and omega, this part of the code is connecting these 2 points. This line of the code is connecting the final 2 points. And similar to before, if xp is less than x2, basically we are looking at this region, use the first w1 value. If xp is greater than x2, if you are looking at this region, use the w2 and use w3 if xp is greater than x3. So this is how you connect n data points iteratively, and it is the simplest and, in my opinion, one of the best approaches. Simple the better. So I hope you like this video. Again, this is just part 1 of the video. We'll dive into some interesting concepts in the part 2. So stay tuned.